This video is designed to give a basic and brief tutorial on how to run and process the data from 2D NMR. This tutorial will also cover NUS processing and phasing. When opening up a 2D NMR spectra, you are greeted by the spectra. To go to the processing menu, use the toggle button in the top right corner. After putting the sample into the sample deck, go to the correctly numbered row in the Delta software, and then name the sample, fill in your name, and then from the drop-down menu select what solvent has been used, as well as selecting a 2D NMR technique. These can be purely a 2D NMR technique, or can include running a proton and a carbon spectra as well, as in this example. If the estimated time exceeds 20 minutes, then schedule the experiment to be run at night. The first stage is to add the zero filling function. This will often be already added to the Y column but not to the X column. To add the zero fill function to either column, make sure the function will be added before the fast Fourier transform function. Then go to the pre-transform tab and select the zero fill function. To select which axis you want to add these to, simply click on the axis box and the selected box will be highlighted with a blue outline, and by a yellow bar on the axis box. Window functions can emphasize features such as resolution and the signal-to-noise ratio. To add a window function, go to the Window Function tab and select a new window function. You can change the window functions using the Change Functions button and selecting a new window function. To delete a window function, simply select the function and press the Delete Function button. The parameters of the window function can be changed by expanding the window and typing in the new parameters. The next step is to use the symmetrization function. Often this has already been added. If not, go to the Post-Transform tab and select symmetrization. This can also be done from the 2D view, by selecting symmetrization from the Action menu. If the spectra is unresolved and has lots of big blobs instead of having clean spots, contouring can be used. To do this, right-click in the 2D viewer and select the Level tool. This will bring up the Level tool in a different window. To change the contour lines, use the slider on the left. Moving it up from the bottom will cut off the lower contour lines, and moving it down from the top will cut off the higher level contour lines. After doing this, the spectra is much better resolved than before. To pick peaks, make sure that the option bar is selected in the option menu and a J value set. Then select the peaks using the Pick Peak button. You can adjust how many peaks there are picked up with the contour tool. To get a readout of the peaks present, go to the Analyze tab and select Print Spreadsheet. If the experiment has used non-uniform sampling, then you will see that both an NUS zero fill and NUS reconstruction function have been added to the task boxes. If they have not, they can both be added by going to the Pre-Transform tab and selecting them from the NUS menu. Just make sure that the zero fill is the last function present and the reconstruction the first. To get to the 1D window for phasing, simply click on the 1D window button. There are two different types of automated phase correction, automatic and machine phase correction. Both are found by going to the Post-Transform tab and selecting Phase and choosing one of the two from the menu. If the phasing has left peaks below the baseline, you can get rid of these by using the Manual Phasing tool. Press the Manual Phasing tool button and drag the pivot point line onto the biggest peak and line it up on the x-axis. Zoom in on the peak and make sure that the pivot point line lines up with the top of the peak. Click and drag on either side of this line to get rid of the peaks below the baseline. If other peaks are below the baseline after doing this, press and hold the Alt key and repeat the above process to correct the first order phase parameter. After this, remember to run the process to store the phase information. If the phasing parameters are known, then they can be changed by going to the Post-Transform tab and selecting Phase, then changing the parameters manually. That concludes the basic introduction on 2D NMR processing. For further information on any of the topics mentioned, as well as some more advanced techniques, refer to JAIL's Data Processing User Manual.
This video is going to go through fluorine decoupling, how to set up the experiments, how to process the basic 1D NMR data, and how to superimpose the data to allow for the decoupling to be seen. To begin, we're going to start with the experimental setup. This will only work if the correct probe has been inserted. Contact a technician if you have any questions on how to do this, and please do not attempt to swap the probe yourself. Once we know the correct probe is in the NMR machine, we need to switch modes. For all basic NMR experiments, that walk-up mode is used. To change this, select the Options tab at the top left corner of the window and select Preferences. This should open a new window. Here, select the Tool tab at the top right corner and scroll all the way down. Here, you will be able to switch the mode by holding down with the mouse to the desired advanced mode. Finish this off by closing the window and logging in using the Data Collection button. After logging in, we can add a new sample by pressing the green plus sign in the top left corner of the screen. This is different to how samples are loaded in the walk-up mode, but it's still straightforward. Start off by writing down the name of the sample. For this experiment, the name MH957 will be used. Select the solvent that was used and the slot the sample can be found in. Finally, verify the sample by ticking the box. After the sample has been loaded, we can start running experiments. To do this, press the Create a Job for this sample button that can be found on the bottom right of the screen, followed by the Add Experiment button. This will open a new smaller window where all experiments are kept. Select the Global tab from the left-hand side of the window and scroll down to select the file of interest. For fluorine decoupling experiments, the HFX2 file contains the basic experiments that can be run, like hydrogen and carbon NMR, and the HFX2CH and HFX3CH contain advanced experiments. Click the green arrow in the top right corner to load the experiment and bring you back to the job section. Here, parameters like number of scans, relaxation time, and spinning can be changed. For the sample that is running, none of these parameters need to be changed, and therefore the Submit Job button is pressed. The experiments in the HFX2 file include a fluorine and proton decoupled carbon NMR, a fluorine NMR, a proton decoupled fluorine NMR, a standard proton NMR, and a fluorine decoupled proton NMR. I recommend also selecting a carbon NMR from the main job section, but for the purpose of this video, the experiments in the folder will be run. Don't forget to press the Submit Job button to add the jobs to the queue. Next, we can access the advanced experiments from the HFX2CH folder. A het core and HOSY will be run just as a demonstration. These experiments usually require some form of parameter changing. For the het core, the Y offset is changed to -145 ppm. This is because when opening a fluorine NMR, we can see that the chemical shift of the fluorine lies somewhere around this value. The Y sweep was also changed to 3.7 kHz per recommendation of one of the employees at Joule. For the DOSY, the Y offset was also changed to -145 ppm, the Y sweep to 10 ppm, and the number of points to 32. This last parameter was changed to shorten the experiment time, but if you have time on your hands, then this won't be necessary. The last thing we want to do is log out and switch back to the walk-up mode. Do this the same way we changed modes the first time round. Please remember to log back in and remove your sample using the red minus sign when your experiment has finished, as the sample slot will be locked and unavailable for use until this is done. The next thing we're going to talk about is processing 1D data. This is not supposed to be a set of detailed instructions, as there is already a video on the Canvas page that shows us how to do this. The first thing I like to do is zoom in. This is done by pressing the magnify button on the top left of the screen and selecting the area to zoom in. Next, we can set the correct reference, or change the value where the 0 value lies. Do this by zooming into the correct area and selecting the button on the top left tab. Click on the middle of the peak to set this as the reference value. Zoom out quickly by pressing the minus key. Next, correct the baseline by going into the Post-Transform tab and selecting Baseline Correct. This job will now appear in the processing list. Click on the play button to execute this job. Another thing we can fix is the phasing, that is, getting rid of these negative peaks. To do this, zoom into the area of interest and press the phasing button shown on the screen. Press down and move the mouse to the left or right to adjust the phasing. Here I'm just showing an extreme example of this. Alternatively, press the A key for this to happen automatically. Select peaks by pressing the X button on the tab, as can be seen. The program registers every peak available, and overall this looks a little messy. Clean this up by changing the baseline threshold. Press the Compute and Show Statistic button first to show the lines on the spectra, followed by the Baseline button. Move the green line up to the point where above which you want peaks to be found and press the cross button again to show the changes. Integrating is done by selecting the Integrating button on the tab. As is seen, the peaks in the 1 to 2 ppm range have all been grouped into one. Fix this by pressing the Select button and hovering over the integration box until a small pair of scissors appears. Drag this line to where you want the integration to end, and repeat this process until you're happy. Another thing we notice from the integration is the hydrogen values that the program has come up with. On this next window, the compound's NMR spectra has been loaded from ChemDraw. We can predict that the triplet present around 4 ppm belongs to the hydrogen attached to the carbon next to the oxygen. This shows up as a triplet as it's next to a methylene group, and should correspond to 2 hydrogens. To change this in our spectra, while still being in the select mode, click on the integration value, which should now appear blue, and change the value to 2 in the normal tab in the options list. Finally, save this newly transformed spectra by pressing File, Save As, and selecting the location and name desired. The last thing we're going to do is look at overlaying two spectra. This works great for emphasizing the results of fluorine decoupling. Open the files that are to be overlapped, and on the Joule Delta tab, select the View, Data Slate buttons to open up a new window. Here, select the Open Spectra button first to select the initial spectra, and the Add Spectra button to upload the second one. The Data Slate window should now contain two spectra of two different colors. Zoom into these peaks by selecting the magnifying button as before. I like to make sure the reference is correctly set before shifting one of the spectra above the other. To do this, select the Hand button from the tab and, while holding down the Alt button, click on the spectra to be moved up. The spectra can be moved as high up as desired. Here will work just fine. Zoom in to see the effect of the decoupling. As this compound is a fluorinated one, where the fluorines are attached to the benzene rings, the only change in peaks are present in the aromatic region, just as expected. Overall, fluorine decoupling are easy experiments to run, and this information can be useful when determining the structure of your compound.
In this video, I'll be showing you how to run a DOSY experiment and some simple processing. In order to set up advanced mode, first access the Tools tab, and at the bottom there should be an option to change the operational mode to advanced. Then you can log in as normal. Enter the name of your compound, select the solvent, enter the slot used, and check the Verified button. Then click the Create a Job with the Sample button. Click Add an Experiment, then find the diffusion category and select the same method as indicated on the screen. Since this is only an initial scan, in the Acquisitions tab, the number of scans can be set to 4. Though this is a small number, this is enough to gauge the attenuation. In the Pulse tab, the gradients applied should be altered. The G-values should range from 10% to 100%. In this case, it would be 30 to 300. You can remove the first value. Spoiler gradients should be enabled, and as indicated, 2 of them should be multiplied by 6. And now you can submit the job. Once the data has been obtained, a 1D slice can be opened so as to view one scan. Here you can see that the phasing needs to be corrected. This can be done by clicking the automatic phasing button and be refined by using the manual phasing controls on the side, as shown. Baseline correction should also be conducted. Now, you can close this window and the settings should be transferred to all the scans. Then by clicking Process File and Put in Data Slate, and going to Expansion and Linearize, you can open all the scans. Here you can make sure that the decay between the signals of the scans is between 80 and 95%. This can be done by picking the peak in one slice of the scan and comparing it to that of another. At least 16 scans can be used. Using more scans may be beneficial. If the attenuation is not as desired, we can increase either the diffusion time or the gradient length. Here we increase the delta to 2.4 so as to increase the attenuation. The opposite can be done if the attenuation is too high. Here, the g-value uses a logarithmic array with start values of 30 to 0.3. The processing again, you should make sure that the phasing is correct and the baseline is corrected too. By increasing this width value to 0.5, some of the noise can be reduced. Once this is done, you can close the window. And going to Analyze and Curve Analysis, you can adjust the threshold as shown and then pick peaks. By selecting all the peaks as shown and changing the mode to Diffusion Analysis, you can obtain the diffusion coefficients. If there are scans that seem to be anomalous, they can be discarded by going to File and accessing the points list, unchecking the points and clicking Apply. The box that says maxima. Open the 2D viewer. Here you can see the compounds that are present and how they separate.